and thank you all for joining. My name is Sergios Gatidis. I'm a pediatric radiologist here at Stanford at LPCH, and I'm medical director of imaging informatics. So my job is to make sure that we can implement not only AI tools, but all kinds of software tools for improving pediatric radiology services and workflows. And before I start, I'd like to say thank you to the great teams that we work with here at Stanford, within the hospital, within LPCH, and beyond. I will talk about artificial intelligence, but without human intelligence, this is all impossible. You need a large amount of creative and motivated colleagues to make this work. And everything I will show today is purely a development from within Stanford. So you will see it's quite impressive what these teams that we work with have been able to achieve over the past years and are still working on. So thank you to all of them. I'm sure I have not mentioned all that are part of the project, but still thank you to all of them. And a big thank you to the Stanford Maternal and Child Health Research Institute for also supporting my work. And I will provide an overview of that towards the end of this talk. Right, let's get started. So if you look at the news, you might think that AI is everywhere, including pediatric radiology. And let's see if that's really the case. So what's the state of AI in pediatric radiology and pediatric imaging in general at this point? There's a great resource which is provided by the American College of Radiology. You can go to their website, and they have these dashboards where you can see how many AI tools are FDA cleared for use in different applications. So there's a lot of numbers on here. The main message, if you look to this bottom center graph, you will see that since 2017, there's a steep rise in the amount of clinical imaging AI tools that were cleared by the FDA for the use in all kinds of different applications, primarily for the modalities CT and MRI, and very prominently for neuroradiology and cardiovascular imaging. So the important detail here is that I only selected the adult population for this graph. And you can all now try to think what will happen if I change this to the pediatric population. I'll give you a few seconds, you can estimate what you will see. Well, it's rather disappointing. On the adult side, we had about 100 FDA-approved tools alone in 2025. On the pediatric side, it's quite stagnating. We have about 9 tools per year. It's less than 10% of the amount that we see for adult use. But of course, children do not need less care. They do not need less support by AI. There's still this significant and quite concerning gap. So that's one of the motivations that we have here at Stanford to close this gap. And wherever industry cannot provide or does not provide solutions, we'll just build them on our own. We will validate them and we'll provide them to others as well. Right, here's another graph showing the same thing. The red part of the bars is the pediatric portion of the FDA-cleared imaging AI tools over the past years. Okay, so you may ask, well, do we really need dedicated pediatric imaging tools? Maybe we can just use adult AI and apply them to children. Why shouldn't this work? Right? We do this sometimes also with other clinical tools, medications, for example. So we looked into this course before starting our journey, and we're still doing so. This is a relatively simple example of an application that is quite common in radiology, which is organ segmentation in computed tomography. This means that we try to identify organs. Here, for example, you can see the lungs, the liver, the skeleton, the brain. And ideally, good organ segmentation should look like this image on the right side, which is the target segmentation. However, if you take an adult algorithm that is supposed to do organ segmentation and that works well in adult populations, the result is seen on the left. So the accuracy completely breaks down. The algorithm is not even able to find the lungs correctly, which is a major failure. And this graph shows that the quantitative accuracy of these algorithms decrease decreases when you look at the younger and younger children. So if you look at the smallest and youngest of our patients, these algorithms perform even worse. We've done some work, and I don't want to be too technical, to understand how we can improve the performance of such algorithms. And the very simple message here is that if you train an algorithm on adult data, then you can inject a small amount of additional pediatric data to the training process, and then you will see tremendous improvement in performance. So, for example, here you can see the ground truth, the target segmentation. If you just apply the adult algorithm, you will see, for example, that in this case, the small bowel was not segmented correctly at all, which is supposed to be this yellow part on the image. But if you add these additional pediatric training data into your training data set, you can suddenly recover the performance that you actually want to have. So it is important to represent children in the training process for these AI models. And I have another example for you, which is also work that's been done here at Stanford. And I just want to give you a high-level overview when it comes to interpretation of chest X-rays, images that look like this. There's a lot of literature and many AI models out there for the adult population again, where you can see that these models have decent performance in identifying major pathologies on chest X-rays. And if you extract features from adult populations of different sources, which we've done here in a simplified two-dimensional way, you can see that these populations overlap quite well overall, even if they come from different hospitals. And this means that AI tools work well on a large variety of adult circumstances. However, if you now take a pediatric source of imaging data, and these are typical pediatric imaging studies, as you can see here on the right side of this panel, and then you look at the features, at the properties of these images, they're completely separate, right? And this tells us already that we cannot expect really good performance from the adult tools if we apply them to the pediatric population. And again, the same applies as before. This is a complex graph, but I will walk you through this. This graph shows what happens if we take an adult foundation model, an adult chest X-ray AI model, and add additional data to improve its performance for a specific population, specific target population. If we switch from one adult population to another, we see that adding a little bit of data helps to adapt to this new adult population. But overall, it's a flat curve, so we cannot achieve too much improvement. However, in the pediatric case, if you start with an adult model, performance is really bad initially. However, if you only add 1 to 10% or even 50% of the training data as pediatric data, then you suddenly get performance that is on par with the original performance on adult data. So same message as before. If children's pediatric data are not represented in the original training data set, you get into trouble, but you can fix this to some degree at least if you take into account pediatric patients and add them to the training data set for AI models. Right. So these are the messages in this technical part of my talk. Children are not small adults. They're different in all kinds of ways in their anatomy, physiology, and pathologies that we see, and they need to be represented in the training data sets for training of these models. So we need specific AI models for children, or at least models that are trained also with pediatric data. And the next portion, I would like to show you how this is done here at LPCH, and just by giving some very practical examples of how we use AI on site. First of all, you cannot just deploy an algorithm online, right? You need to have a process to prepare for that and to validate its usefulness. So we start with an intake process where we formulate the problem, we look into technical feasibility, maybe there are alternative solutions, and we look at the priority of this specific question that somebody, or the idea that somebody brings to us. And then there's a technical part, which is algorithm development. This usually includes collecting data and composing the training and test data sets. And this composition of training data sets very often means labeling data. So there is a step involved where humans need to, for example, identify structures in an imaging data set, or label landmarks or provide reports, right? It can be all kinds of labeling tasks, but this is usually the case in the conventional way of training these algorithms. And then model training is performed and the technical validation of accuracy. In parallel, there's a governance process where here at LPCH, we have an architecture review board and an AI oversight committee whose members look at the application at hand and evaluate safety, feasibility, and whether the tool is appropriate for application in children within our hospital. Right? After these technical and governance questions have been worked through, we usually first go into a test deployment where we look into the IT integration and collect feedback from first users. And finally, we can deploy in production, which also requires monitoring and maintenance. So that's the workflow in general of how we deploy AI tools. And these could be commercial or in-house tools that we build here. So let's give you a few very concrete examples. If you look at these images here, these are all short axis cardiac cine MRI studies, so cardiac MRI imaging here. And you will see three different patients, imaging from three different patients, the top row and the bottom row, and you will think, well, what's the difference? They all look very, very similar. Well, the difference is that the acquisition in the first case takes 3 minutes and requires breath holds from patients. In the bottom row, the acquisition is very fast, below 1 minute, and can be done in free breathing, which is a huge advantage in pediatric populations. So in order to do so, and this is work that's been done by colleagues from pediatric radiology here at Stanford, an AI algorithm, a deep learning model is used to reconstruct images from accelerated acquisitions. And we deploy this method not only for cardiac imaging, but for all kinds of other imaging studies, which greatly accelerates studies for children. Beyond accelerating MRI acquisitions, we can use AI also for automated analysis, for example, here of cardiac MRI studies. And similar to the example I showed before about segmentation of abdominal organs, AI can also be used, in this case, to segment structures within the heart. So, for example, what we usually do is automatically segment the cardiac chambers in order to get functional parameters of cardiac function. And so when we had to work on this for maybe half an hour in the past, nowadays this is done fully automatically, and we may have to adjust a little bit, but overall we save a lot of time and get better reliability of our measurements. Similar example in the field of PET and hybrid imaging is given here. So PET imaging is a nuclear medicine study where a tracer is injected, a radioactive tracer, and the signal is then measured in the scanner. And AI can be used to actually lower the dose of the study significantly. So in this case, you can see a full dose image with some foci here, metabolic foci in the mediastinum. If you just acquire the same data with only about 6% of the tracer dose, you will have deteriorated image quality with a lot of noise. Signal to noise quality or ratio is degraded. But AI can recover signal, so you can reconstruct the appearance of the image if you have enough training data to get a decent quality from a very low radiation exposure. And I don't want to go into too much technical details, but maybe interesting to just show once how these algorithms are usually trained. And in MRI, it's similar. What's usually done is that there is a ground truth, fully sampled or full dose image, that's the target. And then the low dose PET image, or in the setting of MRI, the undersampled MRI, the accelerated MRI, can be simulated retrospectively. So the AI algorithm can then learn to reconstruct the full high quality image from the noisy, low quality image that's faster, that's acquired in an accelerated way or with less dose. And finally, just to show you an example for radiography that we are currently deploying here at Stanford, we have a large number of measurement tasks that we perform every day. We have dozens of studies like this on a daily basis, where as radiologists, we need to identify landmarks in images, quantify distances, for example, here, leg lengths, and then write a report. And so this can be completely replaced by AI tools where the trained computer vision model can identify these landmarks automatically, can measure the distances, and provide the report to us, and we can just sign it. I will show you how this can accelerate our workflows in a second. Right. So these were just few daily examples to show that AI for pediatric imaging exists, but it requires very often that we develop it on site or other pediatric hospitals do so. Right. As I've shown before, it's not enough to just build these tools and deploy them. It's very important, and maybe even more important, to know how well they work while they're active. We want to avoid failure cases where a patient's management requires some correction just because we made a mistake or AI made a mistake. And I want to show you how we do this and how this can be done in general on this, using this example of automated bone age assessment using AI tools. So traditionally, bone age, a patient's bone age would be assessed using a radiograph of the left hand, using an atlas. So there's an atlas also generated here at Stanford by Grulich and Pyle many decades ago, where radiologists can open a book and compare the patient's hand skeleton to an atlas of different ages and then make a determination about the patient's age. Nowadays, and this is something that has been implemented here, developed and implemented here at Stanford for a few years, now we have a deep learning algorithm that can automatically analyze these hand radiographs and then provide an estimate for the patient's bone age. So this works well clinically, but how well does it really work? That's what we want to know while we use this algorithm. And so the trick here is that we use AI in order to evaluate AI. Right? So it's a second level layer of AI on top of the original AI that helps us to evaluate how well these algorithms work. And the ingredients here are that we have a final report for every study. So the radiologists look at these studies, they determine whether the AI was correct, and they correct the report and then sign it if necessary. So we have these final reports. We also have a record of the original AI output. So we can always compare how often was the original AI report corrected by a radiologist, how often did they agree. And we use a large language model to compare these two outputs so that we can flexibly parse the results without having a human read all these reports to identify the numbers and the assessment by the radiologist. And so using this strategy, we can actually look at frequency of disagreement, the degree of disagreement, but also turnaround times. How fast are we reading these studies? So these are the results over the past years with thousands of studies. And here, first of all, let's start with the turnaround times. Before we use this AI tool, you can see that it took about half an hour. These are seconds here for radiologists to sign this report, right? They would have to look at the images, use the atlas, compare the images, and then make their determination and sign the report. This may not take half an hour, but the entire process from acquisition to signature would be relatively lengthy, let's say. And you can see quite suddenly after we deployed this AI tool, our turnaround time decreased to a few minutes at most, right? And these error bars that you see here, these deviations are days where the AI tool was down due to maintenance or some other technical problems. But that's not enough, right? It's not enough to be faster. You also need to make sure that the AI algorithm does a good job. And what you can see here is the percentage of studies where there was a disagreement between the radiologist's final report and the initial AI output. You can see that's an interesting trend. In the beginning, we had in the first weeks of deployment, we had relatively high percentages of disagreement, sometimes above 50%. And overall, over time, you see a gradual decrease. And now, over the past year or so, there's not much disagreement at all anymore. So, on the one hand, you may say, well, that's great. It means that radiologists initially, looked at the tool carefully, and over time they learned trusting the tool. You can also say that possibly this means that there's some automation bias, that radiologists stop evaluating the automatic outcome correctly, and they just believe everything and maybe have forgotten how to evaluate bone age. And so in order to really know what's going on, you need to also evaluate the actual algorithm performance. It's not enough to just look at the agreement between radiologists and the algorithm. There are two components to this. There's a qualitative component. In the case of failure cases where the AI was off, it's important to look at the images and make sure that there's no, let's say, image quality issue or any other issue that leads to this deterioration of performance. Here are a few examples, typical examples of when an AI algorithm cannot be expected to work well. That's typically the case when there's some pathology, anatomical abnormality, or as you can see here, some decrease in image quality. The contrast here is suboptimal, which then leads to the AI making mistakes. And it's important to present these cases to radiologists so that they are aware that when they see these cases, they can expect decreased performance of the algorithm. It's also possible, and we did this here in a retrospective study throughout multiple institutions. This is currently under review. We looked at how well do these deep learning algorithms perform in comparison with humans. And so the reference standard was always 3 human raters. And then we compared a fourth human rater or a deep learning algorithm to this reference standard. And the main findings are that, yes, the AI has similar overall performance. You can see the standard deviation of the error of the AI is similar to the one that the humans show, but the AI has many more outliers, whereas humans usually don't have these extreme mistakes. They don't make these extreme mistakes, which usually are related to these artifacts and qualitative issues that I've described before. Right. So the takeaway message here is that it's not enough to deploy AI tools. Monitoring is as important. And sometimes it's possible to use AI to help with monitoring. So it can be made more efficient. And when assessing AI, it's important to understand what to compare it to. And very often human performance is a good reference for that. Okay. Now you may think that radiology is all about imaging, but actually there's a lot of tasks in radiology that are associated with language, right? Language-based AI. And we all know that large language models are an amazing progress in the field of AI. So also in radiology, we would like, and we do, leverage the properties of these large language models. We did some research on how well these large language models perform in clinical text summarization. So this is a study from about a year ago where we used these language models to summarize clinical text. And we also had summarizations of the same text performed by humans. And then we asked raters, which one do you prefer? Do you prefer the GPT-4 generated summary or the human summary? And we looked at completeness, correctness, and conciseness of these summaries. And overall, what we saw is that it's pretty balanced, but there's a tendency towards preferring the AI-generated summaries when a human rater looks at these summaries. And I think with the new model architectures, the new model models that came out, GPT-5, Gemini, and so on, this will further improve. So summarization is a great application for language models. And this includes also retrieving information from databases. And here's an example of something that's in the beta version right now. It's accessible for our radiologists at LPCH, which is a chatbot that allows us to access efficiently and quickly all the information that we have in our MedWiki, in our clinical documentation and workflow documentation. So the user can ask questions, and then the chatbot would provide an answer based on these documents and also link a link to the original source so that the user can quickly jump to the source and have a version that they can trust, right? Because these algorithms can sometimes also hallucinate, as we know. This is a very practical application. Another example of what's in production right now in our hospital is automated parsing and analysis of radiology reports. When we provide a report, it takes some time until its final sign, but especially for critical results, we want to have a faster turnaround time and a closed loop communication with our providers. It's not easy to monitor how well we're doing in providing this communication. So what we did in this project, we built an AI tool, a large language model-based tool that parses every single report that we write and then determines whether this is a critical result and whether we communicated this result and documented the communication and the turnaround time to our providers. And this is just an overview of the technical realization of this tool. We have Epic as the source for the radiology reports. And at the moment, in a weekly basis, we extract all the reports into a database. And then a large language model reads these reports and determines whether it was a critical finding, for example, tension pneumothorax or pneumoperitoneum, similar critical findings, and also parses whether it was documented that this finding was communicated with our providers. Then we build dashboards based on this information. And just to show you how complex such a project can be, here's an example of just the prompt that we use to prompt these models. So you need to be very specific. We went through multiple iterations of defining this prompt, making sure that it states exactly what we want to have. And we learned a lot from this. The structure of this prompt, and I think this follows structures of prompts in general that we use in clinical environments. We have a core question with introduction. We tell the model you're a radiologist and define the task. Then we need to define an output format. So the model knows to say yes or no and provide evidence for its decision. And then in addition, we have in context samples. This means that within the prompt, we provide examples with correct answers so that the model can also learn from examples, not only from the abstract description of this task. And here you can see what this dashboard can look like. So we have a 60-minute ideal turnaround time or below that for our critical results. And we can now very efficiently monitor that, yes, we are just around or slightly below this turnaround time with our critical results, whereas for other studies, we're clearly above that, which is okay, but we still know that usually our turnaround time for studies is within the same day. And before AI, we were not able to do this at all. So this allows us to have more transparency for our clinical processes. And one language-based application that I'm very excited about is patient-facing. About 2 years ago, I'd say, we partnered with a company that provides these natural language processing-based patient-friendly radiology reports. And you can all try this if you work here at LPCH. If you go to a patient's radiology report and scroll down, you will see a link to patient-friendly radiology reports. And this will open a web page. And you can see the same report that you just read with explanations, with additional explanations. This works the following way. You have the same text, so the text is not changed. But on top of the original text, there are hyperlinks that give you explanations, that define language, and they also exist in Spanish. And this was a phenomenal success, I would say. And we have great feedback from the patient side, the parents, who really appreciate us providing this service to them so that they can better understand and better prepare for their next appointments. Right. So what I wanted to convey in this part is mainly that while imaging AI is very important in radiology, language-based AI may be evenly important just because we have so many applications that rely on language. We write reports, we communicate with patients. And this is why we also look into large language models to help with our services. Well, finally, I'd like to come to one of the exciting parts of my research and talk about the cutting edge of what AI can look like in the future. And this may not say much to you, but this is just a long list of tasks that radiologists perform every day. These are, for example, measurement tasks. And we have hundreds of tasks, right? From measurements to diagnostic evaluations, to protocol preparations, and so on and so on. It's hundreds of tasks, right? This list never ends. And so one option, I think this is what is done nowadays with most AI tools and the FDI cleared AI tools that I showed before. Well, there's a model for every task, right? If you want to quantify liver volume, there's a model. If you want to segment the heart, there's a model. If you want to measure leg length, there's another module. If you get the point. You could have thousands of models for all kinds of different tasks. And here you can already see that this may not be the best idea, right? On the one hand, it's almost impossible to clearly define all the tasks that we have in radiology and in medicine in general. And on the other hand, as you can see, or as I have shown before, the degree of implementation of new models is not as fast, specifically not in the pediatric domain. So we need a different approach to that, right? So this is basically impossible. And this is part of the project that I have the privilege to work on and that's supported by the MCHRI, which is building foundation models for pediatric imaging. And here the idea is different from before. You do not train specific models for a specific task, but the idea is to use large-scale data to train one foundation model, a large model that can then be very efficiently adapted to different tasks. And so the sources for training this model can be images, also text information. It's usually multimodal. And then the training paradigm is also different. Before I explained that for these dedicated, very specific models, there's a step of collecting training data where a radiologist or an expert has to label information. Well, for these foundation models, we use a paradigm that's called self-supervised learning. We try to find the structure, to identify the structure of images and text by having a training task that doesn't require human input. Just one example. One paradigm for self-supervised learning is to use radiology reports and the associated imaging in trying to match the representations that the models give us from text and from imaging. And if you do this over millions of examples, a structured representation of images emerges that can be used for other tasks as well. But there are other paradigms that can be used. And so the big advantage of foundation models is that once a foundation model is trained with a lot of resources, a lot of data, then it requires minimal effort to adapt it to different tasks. It's similar to what we do with large language models. These large language models require enormous computational effort. But once they are trained, you can prompt them easily to, let's say, write a poem or summarize a research grant or review a paper, right? That's all possible with these foundation models just because they were trained in this general self-supervised way. And the goal in this project is to build these kind of foundation models specifically for pediatric imaging, which may hopefully solve some of the issues that we have with a limited availability and accessibility of AI for children. And here's one example of what this could look like. So this is just a quick prototype that I put together of one of the models that we're working on right now. And this model can understand text, can understand instructions, and can then perform a task on imaging data, right? It's not a purely imaging-based model. It's similar to the visual language models that you can see with GPT or Gemini, where you can interact with images and ask questions about images. So in this case, I ask, let's see, what did I ask? Where's the stomach, right? And then the model can identify the anatomy within the image. That's a simple example, but the idea is that these capabilities will be enhanced over time. And then if you can find the stomach or if you can identify anatomy, then the next easier step from there is to identify, for example, pathology. Right. So I have great hopes for foundation models. I think this is what the future of AI in radiology will look like. And it will be a very interesting project to work on. So you can expect that within the next years, there will be more products available also by companies that are not specific for a single task, but they may give the user the ability to modify to specific tasks that they want to use, similar to what large language models do. Right. And with that, I'm already at the end of my presentation, and I hope we'll have a great discussion. Thank you.
Thanks so much, Sergios. That was a fabulous presentation. We have a host of people on this call that I hope have a wonderful array of questions. Um, we don't have any in the chat at the moment, but if anyone wants to come off mute and ask a couple questions, now's the time.
Answer. This is Tony. Great talk. Can you talk about, so Michelle Mello talks a lot about risk assessment, legal risk assessment in implementing. Do you have a sense about how to mitigate that in when we implement the foundation models and how we're addressing that?
Oh yeah, that's a great question. I think the main question is, what's the purpose of a model? Is it fully autonomous, or is it supporting the work of an expert? Right? If it's a support tool, then not much changes in terms of where the risk is. The radiologist still needs to make their own assessment and provide a report. Right? In that case, the risk is the same as before, but we hope to have some enhancement of the abilities of the expert. If we have a fully autonomous agent, then the risk assessment changes completely. And this is why at this point, we actually do not have fully autonomous diagnostic agents in radiology. Every single diagnostic processing tool that we use needs to be assessed either by a radiologist or by another expert technologist who then provide the final output. There are some, I think in order to mitigate risk, the best strategy is to have good monitoring in place, right? If you can prove that your monitoring has a good probability of catching outlier cases and identifying cases where there may be failure, you can have higher confidence in deploying also fully autonomous tools. And I guess the main question is, how high is the internal risk of the application itself, right? If I perform leg length measurements, well, the risk is somewhat limited. But if I assess, propose therapy for a patient that may have side effects, the risk may be significantly higher. And yeah, so my main answer would be overall that monitoring needs to be in place and risk needs to be assessed based on the internal risk of the application. We have the AI Oversight Committee at LPCH where we discuss these questions in order to make sure that this is implemented correctly.
Yeah, that's great. If no one else has a question, I have another one, which is about promptology. The things you interact with the computer and the things the prompts, how it seems like it's very difficult. And will that be a way of learning in the future for physicians about how to interact in terms of how to communicate the prompts you give versus what you want to get back and that sort of thing?
Well, yeah, so training is certainly a huge part of what we have to do for all of us. So when you think about the prompt specifically, a prompt or part of the prompt can also be part of the system settings, right? It doesn't have to be purely defined by the user. But ideally, we would like to have some flexibility, right? You would want to ask a question or guide your tool towards resources. This will give you more flexibility. This comes with additional risk. So I think that's where education plays a big role. And you may be aware of ChatEHR, which is a tool available at at Stanford Healthcare. In order to use ChatEHR, you need to go through a 30-minute
Right.
a video and answer some questions to be aware of the risks and how to use the tool. So I think this is the best version of how to implement. Beyond, of course, having monitoring in place, making sure that there's good technical validation with benchmarks before deployment, and also having, I think that's very important, qualitative assessment of performance by humans, at least for a subset of cases, right? Beyond the quantitative assessment.
So I think that's going to be board scores in the future. Will be also have to be prompt EHR. Will have to be to figure out how to interact with AIs.
Well, it's a skill, right? You learn how to present a case to a colleague, right? You need to learn how to interact with AI. Hopefully, AI will become better up to a point where there will be a lot of flexibility and less risk, but you still need to know what you want to get out of the system, and you need to understand where this information can be found, for example, in order to make it work efficiently.
We're getting a lot of kudos, Sergios. Any other questions? All right, going once, going twice. Can't thank you enough for the time. Really wonderful presentation. This will be recorded and posted on our website as well as our YouTube channel. And look for our upcoming seminars in the new year. But hope everyone has a great holiday season, and we'll see you soon. Thank you again.
Thank you all.